experience or talk on Wednesday with the current showcase? No one went? Anyone?
Well,
Packaging people?
I got an interview with Lloyd.
Lloyd?
Lloyd.
Okay. Nice. Anyone else? There's a lot of packaging people over there? No? Goodness, you guys are so shy. Anyways, so hopefully you guys were able to make good contact, those of you who went. Just an idea, how many of you went there? Almost all, everybody. Okay, half of you. Okay, so last time what we started to do, we started to establish some basic concepts that will allow us to study and understand vibration and use some, I would say, develop some tools for design of packaging system for protection. Okay, so we talked quickly about some basic mathematics of motion. We established the impact velocity, which we're going to hopefully not forget or put aside a little bit and revisit a little bit later. And then what we did last time was first talk about vibration. Okay? And we mentioned that with mechanical vibration, what you have is you have dynamic compression and also sometimes large acceleration that can be susceptible to cause product damage. Okay? And the thing is also important is if you do have product damage that are due to acceleration, one thing you should notice during the pattern of damage and occurrence is that this should be pretty systematic because vibration will be there all the time. So unless you have like a very unique route, but typically if you have road transportation and the vibration associated with road transportation cause damage to your product, it's going to happen pretty often because you cannot go without it. Okay? So what we will do, again, to guide you through the process here, we're going to talk about equations to describe vibration, pretty simple stuff. Then we're going to talk about free vibration, okay? And then we'll go to forced vibration. What's really important for us would be forced vibration, where you have the movement of the truck bed, for example, that actually create the vibrating motion. So free vibration, as you will see, is the classic example of the pendulum or the guitar string that you pluck and start vibrating on its own. Okay, so obviously that's not what happens during distribution, unless you have. It's not going to happen. Even in a shock, you have kind of a forced impact that created the motion. So last time we introduced the Hooke's law for spring and mass system because we're going to develop our analysis based on the spring and mass system. So I was about to do a schematic, but we were kind of stretched on time. Okay, so we stopped. So let me do this here. Okay, let's see, maybe I should. Make sure we have things done here. Three different states for our system here. Okay. Okay, so each of these systems, what we'll get. Force from the spring here. We'll have zero force here. Force from the spring here. this. So receiver, we have stretched, relaxed, or if you want equilibrium. And here we have compressed system. So in this case, you guys understand these pretty straightforward, okay? And the assumption that we had when we, before we start to talk about these, is we established for this very unique case, to establish some basic things. We assumed that our mass was like on a frictionless mat. You can have like we assumed that there was no friction. Obviously, horizontal, we neglected gravitational acceleration, okay? And we assumed that our system was ideal. We had no loss in the spring or anything like this. So in a way, thinking about this system, and if it started vibrating, and you can think of initially you may stretch the system, okay, and then you let it go. And the idea of a free vibration, okay, is that you have no dampening, none of these effects, and the system will vibrate and oscillate between those states infinitely. So how we represent this, okay, we have time. We're going to have something that will look like this. Okay. That will be our displacement as a function of time. So we can, as you'll see, we're going to use a sine wave to represent most of these. Obviously, a cosine works as the same thing, but it's just a little bit arbitrary. It doesn't matter where, packaging application, where the vibrations start, what is the amplitude at T0 is not a big deal because we're looking at a long time. So obviously here, okay, we define a few things, okay. We have T, which is the period. You know this, okay? And this as units, okay, of seconds. That's the time it takes to complete a full cycle. The frequency is 1 over the period, okay? We talk about the frequency quite a lot. This as units, therefore, 1 over seconds or hertz. Here, A is the amplitude. Obviously, this has units of meters, okay? Meters depending on units of length, okay? So, obviously, I'm not going to rewrite what the definition of a period is. You should know the time it takes to complete a full cycle, okay? You should be able to know this and remember. The amplitude, there's different ways sometimes to refer to the amplitude, okay? In this case, you can have 0 to peak amplitude or peak to peak amplitude. So the amplitude here, okay, if we're talking 0 to peak, the amplitude is going to be A. If you're talking peak to peak, the amplitude is going to be 2 A's. Okay? Yes?
Is that an S?
Yes, these are S's. Or seconds.
How will we know which amplitude you're referring to?
So unless it's really strictly, unless it's specified, it's always going to be 0 to peak, okay? It's just that some document you may read, you can say peak to peak, so you need to know what it means by this, okay? So, very good question. So mathematically, how do we represent this? So, that'll be our amplitude, sine of pt. We define these things here. T is the time. P, okay, is what's called the angular frequency, or sometimes circular as well. Frequency. We have here amplitude. And obviously, this is your displacement. With respect to equilibrium. Position. Yes.
For frequency, it says 1 over S, and then is that another S or and?
Here?
Yeah, what's that?
Or.
Or H?
Hertz.
Oh,
HS.
okay.
Hertz. So, good. So the angular frequency, what is this thing? Okay. So, in a way, you know that trigonometric functions, sine and cosine, have a period, right? What's the period of these functions? 2 pi. Good. Okay. So, in a way, we know that if we have p times t, okay, this should be equal to the period of function, 2 pi, right? This is the period it takes for our system to go from equilibrium, okay, go all the way up, all the way down, and go back to its initial state. So, knowing this, okay, that also means that p times 1 over the frequency, which is the period, equals to 2 pi, and therefore our angular frequency is always going to be 2 pi times the actual frequency of the vibration. Okay, so if we're going to be dealing with like a free vibrating object, we're going to see that it's going to vibrate at its natural frequency, and that means the angular frequency is going to be 2 pi f. In this case, it's going to be the natural frequency. If you force something to vibrate at a given frequency, that means its angular frequency is always going to be given by this. It's going to be 2 pi f. Relatively straightforward. So, obviously, this is good that we know the position of the time, okay, but for packaging applications, the displacement x of t is usually not the most important parameter. So, can you tell me one occasion or one type or one cases or some situation where the displacement might be of importance for packaging application? Think about it this way, okay? The way to think about a spring and mass system is that the product is the mass and the spring is a cushion, okay? So when do you think the displacement might be important?
When the product is thrown on the ground, how much the cushion.
Okay, that's good. So actually this is a good point, okay? Because one thing you don't want to be confused is the following. What is the purpose of a cushion in the packaging system? To dampen the impact. So use a cushion to protect against shock, not vibration. But the cushion, by being there, influences the behavior when you expose it to vibration. So, what did you say again?
Like when the cushion, when it throws.
Okay, so good. Okay, yeah, that's what you said. Okay, so it's similar. But the thing is, so this will happen on an impact. So when you have vibration, what you don't want it to happen is that amplitude to be so much, okay, that the cushion bottoms out. Okay? That means that it compressed so much that there's no more working length, and it's basically now hitting a hard surface every time. Okay? Obviously, for most product, it's never going to happen. You need to have like a pretty heavy product, okay, with a cushion where vibration is really going to do that. Okay? But that would be here, except if vibration are so large that the product bottoms out. Okay. So most of the time, displacement is not a big deal. Okay, the most important factor is acceleration. Okay, so if we have this guy, okay, that displacement, that means that the velocity is that variation of x with respect to t, so it's the first order derivative of x with respect to t, so it's going to be AP cosine of pt. Finally, the acceleration, actually these are all functions of time as well, okay? Acceleration as a function of time is going to be equal to d square x dt square or dv dt. If you take that derivative again, you end up with minus a p square sine of pt, okay? So what you see here, obviously, is that, obviously, if you remember, if you look at the sign here, so the acceleration is 180 degrees out of phase with the displacement. That means when you have a maximum displacement, a positive displacement, you have a maximum or minimum acceleration. It's going to be negative, and vice versa. You also see that when your position is at equilibrium at zero, this is where you have zero velocity, zero acceleration, and you have the maximum velocity because cosine is going to be maximum there. So this is all nice, but typically, again, we're doing packaging application here, and things get obviously really complex pretty fast, okay? Because we're not dealing with a simple mass and spring system. There's a lot of components, a lot of variable, and so on. So what we are really after here, okay, is the following. Okay, I can actually write it down here. That means that the maximum acceleration, okay, is going to happen when that sine function takes its maximum value, which is 1, okay? So it's going to be plus or minus a p squared, okay? Typically, we just use the positive value, okay? And just circle that, but that will be very important. That means that typically when we ask for acceleration, we kind of assume we want to find the maximum acceleration, and it's going to be equals therefore to 2 pi f squared like this as well. So that simple equation allows us to link frequency and maximum acceleration in the case of a simple sine wave that follows basically an harmonic motion. So it's pretty straightforward. So any question on this? Good. Okay. So next step. We have a few more definition, okay, on the cushion side, and then we're going to go back, okay, and really explore
I have a question. Why'd you circle the plus in A max?
Because typically, what I mentioned is that we're just looking at the magnitude of the maximum acceleration. So it's just we'll focus on the positive value. Focus on the positive in this. Good. So one concept, the next concept that we're going to introduce here is the concept of static deflection. Okay. This we're going to represent by delta st. Okay. And this guy as units of meters. So the static deflection is, by definition, the displacement at rest of a mass on a linear spring, or if you want, cushion.
Are the units mass? Is that a W?
No, it's M.
Oh.
Goodness. Sorry about that. So, good. So if you just had spring, obviously, draw that as simple as possible. Bless you. So if you look at this guy with a mass on the spring, you do the free body diagram on this. What you're going to have is you're going to have its weight, okay? You're going to have the force of the spring, okay? It's pretty simple, okay? If it's at rest, so that means there's no acceleration. That means the sum of the force are equal to 0, okay? So in here, we can find that the force of the spring is going to be minus K is minus delta ST is going to be equal to the weight, okay, mg, okay? So this is obviously the weight of our object. So from there we find the static deflection, okay, is equal to the weight divided by the spring constant. And again, that's something it's easy to do in the lab. We're going to just use that factor quite a lot in our calculation. And sometimes when we start doing analysis of motion during vibration and so on, we'll have to remember about that static deflection, because when we analyze the force of the spring, we need to realize that once the mass has been placed on it, and there's basically a new equilibrium, but at equilibrium, meaning if it's sitting there, there's a force associated with that spring. Okay, it is pushing the mass upwards according to its weight. Only where the spring is at its natural equilibrium position, there's 0 force here. So the next step, again, this is a bunch of little definition here, but hopefully when we're done with this, it's going to flow better. Did you guys have a question?
I don't understand what's the point of, you just end up getting like the mass, right, of the, if you do, that's a force balance, and you're letting the forces equal to 0, right?
No, they equal to each other. Yeah, the sum of the force equal to 0. And if you have this, it's at rest, that means the force of the spring equals the weight. So it's just a definition of the static deflection.
Okay.
That's it.
Okay.
So the next thing is what you can be faced with sometimes, okay, is combination of spring or cushion. And again, I always use that spring/cushion because it's packaging application is going to be cushion that we represent by spring. Okay, you can have cushioning material that will be placed in parallel. Okay, and that happens quite a lot if you have a bunch of cushion on corners of your box or your product. So you're going to have parallel cushion or spring. Okay, it will look something like this. So cushion like this. What you have here in that mass, you have its weight going down. Okay, and I'm going to call that F1. So what we want to find is that for our calculation, we may have to find an equivalent spring constant for this system, okay? That's why we're going to look at these things. So what we know here is that the equivalent force, okay, is equal, okay, to the weight, and that's equal to the sum of those two forces, F1 and F2. So the force of that equivalent force here, okay, is going to be K sub E times a certain displacement, okay, that would be equal to K delta X plus K delta X, okay. Here we assume that we have same material for both cushions. So that means if you have all of this, you need to understand that all of these displacements are the same. So they all simplify, and you end up with an equivalent K that is basically the sum of these K's, or in this case, just 2K, like this. So if you have cushion in parallel, you basically have to assume that the sum or the equivalent spring constant will be the sum of the K's for all of these cushions. Again, there's a lot of assumption here, and things are not always this way. So you may have to trick this down a little bit, but obviously this assumes that the mass of the product is uniformly distributed, okay? So if you have a product that is not, the center of mass is more on one side than the other, so you may have different deflection and so on. This is basic stuff, okay? Basic tools to us as well to start our analysis, and then you can go to more, okay? If you have cushion now in series, okay? We have something like this, okay? So what you're going to be dealing with in this case, you have the weight and you have the equivalent force, okay, from your system. So in this case, the total delta X, if you want, is going to be equal to delta X1 plus delta X2, okay? Yes?
What's the delta X on the parallel one? Where's that in the diagram?
It's just a deflection from the spring.
Oh, because it goes back to equilibrium, you're saying it's...
So it's basically, when you put the mass, there's a deflection, right?
Okay.
From, and that would be the small displacement that the mass causes to the spring.
Okay.
Okay? So in here, when you put the mass on, so you're going to have the weight that exerts the force on the spring, and since they are in series, their displacement will be different if they have different spring constant, okay, which is usually the case. And that means the total displacement of the mass, if you wanted static deflection on that thing, okay, is the sum of both of these deflections for both spring constant or both cushion, okay? So the thing, though, is that in here, the equivalent force is equal to the force of the first spring, is equal to the force of the second spring, is equal to the weight. They're all equal to each other because they are all in series. So the equivalent force that we are looking at after to find Ke, okay, is going to be Ke times delta x total, if you want, and this is going to be equal to W. That means that delta x total is going to be W over Ke. F1 is going to be K1 in this case times delta x1 is going to be also equal to W, so we can express all these displacement as a function of the spring constant and the weight. Okay? Delta x1, weight over K1, and lastly, K2 delta x2 equals to the weight. That means that delta x2 will be equal to the weight divided by its stiffness, K2. So if we call this, let's see, equation, let's see, I use equation A. We'll replace that in equation A. What we have is W over Ke going to be equal to W over K1 plus W over K2. You probably saw where this was going. When you're dealing with series and parallel, you always have one is the sum and the other one is the inverse of the equivalent is the sum of the inverse. It can be heat transfer or circuit, all of these things. So all of these W simplify. This, and you can play with this all the ways you want. All of these are the same thing. So that's the idea here.
Are you saying that the springs are weightless?
That's a good point. Yes, it is an assumption here. It's on my page. I did not write this. It's not necessarily weightless, but very good point. Okay. I should have it circled bigger here. That's the first here. And in both cases, okay, you can remember that the static deflection, okay, can always be equal to W over K. Whatever it is for that system.
Delta x1 is equal to delta x2, right?
Not in this one.
So
It depends. If they're the same, yeah, but if they are different, if they have different spring stiffness,
okay.
they're gonna deflect
That's what I thought.
different. So here it makes it pretty complex. If we have different spring constant, okay, which typically is not always going to happen because if you have cushion in parallel, they're usually going to be made of the same material. If you have, let's say, styrofoam on the corner of the box, they're going to be pretty much the same, okay? But if you have them in series, then you can have like just thinking about the corrugated itself, okay, and styrofoam or whatever you have in there, they will be in series and they will have different spring constants. Okay, so that's good. So the next thing is something that is important if we design cushioning materials. How do we establish the spring constant, okay? And how does it link to the material and its property. So we want to link, okay, spring constant, this is K, and the modulus of elasticity. This guy here is capital E. So, there's a few mechanical engineers here, they should have seen that. But the modulus of elasticity always is also referred to sometimes as Young's modulus. Okay, so let's define this. The modulus of elasticity is a parameter that relates the stress, call that sigma, and strain, call that epsilon, of a linear cushion material under a level. It's time to write this down. Okay, so mathematically, this is equal to stress over strain. So, if you remember, stress is a force over an area. In this case, I'm going to call it 0. And a strain is a deformation over an initial dimension. Okay, I'm going to define all of this for you. So, obviously, this is the modulus of elasticity. This guy here is a force. This guy here is the area on which the force is applied. This guy here is the initial thickness of the material. And this guy here is the deformation. I'm going to use this as an absolute value. Obviously, if you're in tension or compression, you can define this as positive or negative. That's a B. A. Yes, absolutely. Okay, so what's the idea? What we want to do here is to link that to our spring constant. Okay, so getting with this, we distribute this a little bit, we have that the force, okay, times L0 over delta L A0.
Does force and delta L are always positive?
That's what I said. So the force, the thing is, you can, if they are in compression or in tension, they might be different signs, but here we're just looking at the absolute value.
Okay, always absolute value.
Typically, you know. So, so that's what it looks like. Now, what we want to do is reorganize this again, so we can have the force that would be equal to our modulus of elasticity, A0 divided by L0. And you can regroup these, and that's multiplying by delta L. Yes.
Sorry, another question. Is it the same to compress and to stretch? Does that formula know that? Because it could, in my head, it could like be different. It could be harder to like compress it, but it could be easier to stretch it. But that could be just.
It might depend on the material, but if for linear material, if you think of a spring or something like this, it would be the same.
Okay.
So if you see this, you should find that this is equivalent, okay, this equation, K delta L. Okay, so in a way, the spring constant of a cushion, okay, is going to be given by its modulus of elasticity. The area that is used to bear the force or the weight, okay, and its initial thickness. So that means that if you go in the lab, okay, and you want to have, let's say you did some calculation, and you want a certain stiffness of the cushion, a certain K-value, then you can basically go and cut the cushion size you think you need. If you know its modulus of elasticity, okay, you will know what thickness and area you will need. So just to make sense of this, I think we're going to finish with that little example just to apply this. Let's say you have, let's write this down. So let's take a slab of linear cushion material. With a modulus of elasticity equals to 172. 72 times 10 to the 2 newtons meter squared. Continue here. If we cut a piece of 12 centimeters by 12 centimeters by 6 centimeters, and we use 12 by 12 side as the weight-bearing area. What is K value of the cushion? Again, it's really simple. It's something I can ask you in an exam. You're going to be given all of these equations. But if you have a problem and the K is not given, you may be asked to calculate it if you have the modulus of elasticity. So again, it cannot be simpler than that. Okay. The area here in that equation, okay, A0 is the area on which the weight is applied. So here, if we use meters, okay, that will be your area. The initial thickness of your cushion is 0.06 meters. And your modulus of elasticity is 172 times 10 to the 2 newtons per meter squared. So if you plug in all of these in the equation, so we'll find that K value will be equal to E A0 over L0. If you calculate this, you'll find a value of 41.28 newtons per meter. The units of K are again newtons per meter, and that's it. So it's really straightforward. The only thing you have to understand is what is the area that bears the weight, and what is the thickness, initial thickness of the cushion, and where it goes. So this is before you pack everything and you stop listening, okay? Unless you stop listening already. So we kind of done with like cushion and quick definition. Okay. What we do next is we're going to look at how we can describe physically and mathematically, do an analysis of a freely vibrating system. So that will be our first step in our analysis. Then we're going to look at what if that vibration is caused by a forcing motion. We're going to do force vibration. And finally, we're going to look at a real system where you have force vibration. There's also damping, because that's what happens in real life. You have dampening as well, a trend to decrease the amplitude with time. So that's it for today. Have a great weekend, and I'll see you on Monday morning.